Captions in English, please. So this is the 6th video of chapter 8, and it will be about the mass percent composition of compounds. So sometimes we don't know the identity of a chemical compound. Let's say that we did a chemical reaction and we got a mixture of products that we separate out. We say that we purify them. We will then need to confirm the identity of each product. So we could use physical properties like melting point and boiling point to give us some information. We can also determine what elements are in the chemical compound and in what ratios. And this is called elemental analysis. So elemental analysis will give us the chemical formula of the compound. So the mass percent composition or mass percent of an element in an element is the element's percentage of the total mass of the compound. So you see the formula below. The mass percent of element X in the compound is the mass of element X in that compound divided by the mass of the compound times 100. So the mass percent of each element can be determined using a variety of instruments. And the most common techniques involves spectroscopy. So finding the mass percent composition. Let's go through an example to see how we do this. A 0.358 gram sample of chromium reacts with oxygen to form 0.523 grams of the metal oxide. So what is the mass percent of oxygen in the metal oxide? So the law of conservation of mass tells us that when you have a chemical reaction, matter is conserved. So the mass of the reactant should be equal to the mass of the product. So that means here the mass of the metal oxide should be equal to the mass of the chromium plus the mass of the oxygen that reacted to it. And so if you want to find the mass of oxygen, you do the mass of the metal oxide minus the mass of the chromium you started with, and you will know the mass of oxygen that has reacted with the chromium. So that's 0.523 grams minus 0.358 grams, and that's 0.165 grams of oxygen in this sample. So that's the mass of oxygen in the sample. And now we can calculate the mass percent of oxygen by doing the mass of the oxygen in the sample over the mass of the metal oxide, the compound, times 100. So it's 0.165 grams of oxygen over 0.523 grams of the compound times 100. And when you do this in your calculator, it's so 0.165 divided by 0.523 times 100. So don't forget to multiply by 100. Sometimes people forget that it's a percentage and that you need to multiply by 100. So the calculator answer is 31.548, etc. And here, because the given masses, both of them have 3 sig figs, so we need to keep 3 sig figs. So 31.5 is the percentage of oxygen in that compound. And so what is the mass percent of chromium? Well, instead of doing this whole formula where you do the mass of chromium over the mass of the metal oxide times 100, because you know there is only oxygen and chromium in your sample, what you can do is simply do the 100 minus 31.5 to get the difference, and the difference should be the percent of chromium, because you know, both elements, when you add up their percentages, you should reach 100% if you have only those two elements in that compound. So let's use the mass percent composition as a conversion factor. Yes, we can use the mass percent composition as a conversion factor between grams of a constituent element and grams of the compound. For example, the mass percent composition of sodium in sodium chloride is 39.34%. So how can you write this mathematically? It means that 39.34 grams of sodium are contained in 100 grams of NaCl because it's a percentage, so it's always referring to 100% of the whole thing. And here the whole thing is the sodium chloride, it's the compound. And so the percentage that is given is the percentage of sodium. So that means it's the mass of sodium in 100 grams of the sodium chloride. So written as an equality, it looks like this. 39.34 grams of sodium equals 100 grams of NaCl. But you want to read this. Of course, it's not equal. What it means is the equal sign here refers to, you can read it as are contained in 100 grams of NaCl. But this is an equality, and then we can use it as a conversion factor when we write this as a fraction. So in a fractional form, this leads to two conversion factors between grams of sodium and grams of sodium chloride. So either the grams of sodium are on top and the grams of sodium chloride on the bottom, or vice versa. So you can use this as a conversion factor to change, grams of sodium to grams of sodium chloride or vice versa. And let's use this example. How much sodium should we consume per day? And so the FDA recommends that adults consume less than 2.5 grams of sodium per day. How many grams of sodium chloride can you consume and still be within the FDA guidelines? Because typically we consume sodium in the shape of sodium chloride, which is a table salt. And we know now that sodium chloride is 39.34% of sodium by mass. We saw that in the previous slide. So what is given here? The given amount is 2.4 grams of sodium. That's what you aim for to eat per day. We want to find the mass of table salt, basically, sodium chloride, that this is, because we eat sodium in the form of salt. The relationship is given by this mass percent composition of sodium in NaCl. And we know we have 39.34 grams of sodium in 100 grams of NaCl. So that can be written as this equality. So the concept map will look like this. We have grams of sodium to start with, and we want to find grams of table salt or sodium chloride that we can eat per day. So we have a relationship that relates these two. So it's going to be only one conversion factor here. And so the conversion factor will be having the grams of NaCl. It's not grams of NaCl, but grams of, so let me fix this. So the conversion factor is 100 grams of NaCl over 39.34 grams of Na, because we want to cancel the units of grams of sodium that are given in the given amount. So the solution is you take the given amount of 2.4 grams of sodium, that's in the numerator, and you multiply by the conversion factor. And it's written such that you can cancel the grams of sodium, and you're left with grams of sodium chloride, which is what you want to find. In the calculator, you do 2.4 times 100 divided by 39.34. And the calculator answer is 6.10066 grams of NaCl. Here we have two sig figs in the given amount, and the 100 and the molar, the mass percent of sodium are, with more sig figs. So the limiting amount is from the number of 2.4 grams, the given amount. So we keep the 6 and the 1, and what comes after the 1 is a 0, so we keep the 1, 1. And so we need to consume 6.1 grams of table salt maximum per day to not exceed the recommendation of 2.4 grams of sodium per day. So we can also calculate the mass percent composition from a chemical formula. Earlier, we saw an example of how we calculated the mass percent composition from a sample, from experimental data. But you don't need experimental data to find the mass percent composition of a compound. The chemical formula and of course the molar masses, the periodic table with the molar masses are needed. So based on the chemical formula, the mass percent of element X in a compound is, so the mass percent of element X, you take the mass of element X in 1 mole of the compound over the mass of 1 mole of the compound. So basically you take the mass of element X, in your formula and over the molar mass of the compound. So everything in grams per mole. And then multiply by 100 because remember it's a percentage. So you need to multiply by 100. So for example, if our compound is NaCl, we can calculate its molar mass by adding the molar mass of sodium to 22.99 grams for 1 sodium plus 35.45 grams for 1 chlorine. Added together, it's 58.44 grams per mole of NaCl. So that's the molar mass of the compound. Now, if we want the mass percent of sodium in NaCl, so there is only 1 mole of Na in NaCl, right? Only Na and 1 Cl. So you take the mass of 1 mole of Na and it's 22.99. And that will be the mass of Na in 1 mole of NaCl. So then to calculate the mass percent, you do the mass of Na in 1 mole of the compound, and it's 22.99 grams, over the molar mass of the compound, 58.44 grams for NaCl, times 100. And you will come up with this number, 39.34% of Na that we've seen earlier. So that's how you can calculate the mass percent composition using the chemical formula. So let's practice that with this example. Calculate the mass percent of chlorine in C2Cl4F2, which is a Freon 114. This is a gas used as a refrigerant, but these are banned now. So we know that the mass percent of element X is calculated by taking the mass of element X in 1 mole of compound over the mass of the compound, the molar mass of the compound, times 100. So we need to find out the molar mass of the compound, C2Cl4F2. So we have 2 carbons, so 2 times 12.01 grams per mole of carbon, and 4 chlorine, so 4 times 35.45 grams per mole of chlorine, plus 2 fluorine, so 2 times 19.00 grams per mole of fluorine. When you add this all up, it's 203.82 grams per mole of C2Cl4F2. So that's the molar mass of the compound. So now let's find the portion of the mass that is only due to chlorine. And so the mass of chlorine in C2Cl4F2 is the part that has 4 times 35.45, because only that is due to chlorine. And that's a total of 141.80 grams of chlorine per mole of C2Cl4F2. So now we can plug in these values in the formula. And so the mass percent of chlorine will be 4 times the molar mass of chlorine, which we calculated just above, over the molar mass of C2Cl4F2 times 100. So we calculated those intermediate answers. So 4 times the molar mass of Cl is 141.80 grams. Molar mass of the compound is 203.82 grams multiplied by 100. If you do that in your calculator, divided by 203.82 times 100, The calculator answer is 69.57119, etc. And here we have, it looks like the intermediate answers have 5 sig figs, but really they came from numbers that had only 4 sig figs. If you look at the molar mass, when we calculated the molar mass, they all had 4 significant figures, you know, the 12.01, the 35.45, and the 19.00. So you want to keep the original precision. So it's only 4 sig figs in the end, and it's 69.57%. Because of the molar masses having only 4 sig figs. So that's the mass percent of chlorine in this Freon 114. So some word here about fluoridation of drinking water. So fluoride, we know, strengthens tooth enamel, which prevents tooth decay. But too much fluoride can cause teeth to become brown and spotted, a condition known as dental fluorosis. So extremely high levels can lead to skeletal fluorosis. So this means the fluoride would replace the calcium in the bones. So you don't want that. And so the scientific consensus is that, like many minerals, fluoride shows some health benefits at certain levels. So we need to keep it at certain levels. And for fluorine, it's about 1 to 4 milligrams per day for adults. But it can have detrimental effects at higher levels. And so adults who drink between 1 to 2 liters of water per day would receive the beneficial amounts of fluoride from fluoridated drinking water. So officials usually have decided to allow fluoridation of water, of drinking water, so that the whole population gets its amount of fluorine, you know, by drinking water. And so fluoride is often added to water as sodium fluoride, NaF, which is also a compound that is typically in toothpaste. So what is the mass percent composition of fluoride in NaF? So to calculate the mass percent of fluoride in NaF, you take the molar mass of F, and here there is only one F per formula, so just 1 time the molar mass of F over the molar mass of the compound, and here it's NaF, times 100. So the molar mass of fluorine is 19.00. The molar mass of NaF is 19 plus 22.99, and all of this multiplied by 100. And if you do that in your calculator, you get a mass percent composition of fluorine in NaF of 45.25%. So, and it makes sense. If you look at the molar mass of NaF, it's made of basically fluorine is almost 20 and sodium is a little more than 20. So for fluorine to be a 45% 0.25 you know, percent by mass of NaF, it makes sense. So how many grams of NaF should be added to 1,500 liters of water to fluoridate it at a level of 1.0 milligrams of fluoride per liter? So we will solve this as the usual conversion problem or dimensional analysis problem. So the given amount here is the amount of water that we try to fluoridate. 1,500 liters of water. We want to find the mass of NaF in grams that we should add to this amount of water to fluoridate it at a level of 1.0 milligrams of fluoride per liter. So this you know, level of fluoridation can be written as a conversion factor because it's milligrams of fluoride per liter. It's per liter of water. So in 1 liter of water, we want 1 milligram of fluoride. That's what it means. So mathematically, we can write this as 1 milligram of fluoride equals 1 liter. That's what we want. Because we want the grams of NaF, we will change those milligrams of fluoride into grams. So we will need to change the milligrams into grams using the definition of the milligram. And so 1 milligram is 0.001 gram. Once we have the grams of fluoride, we can then use the mass percent of fluoride to get the mass of sodium fluoride. And so we need to use the percent composition of fluoride in NaF, and that's 45.25 grams of fluorine in 100 grams of NaF. So that's how you want to use the mass percent of fluorine. So the concept map will look like this. We have liters of water. We want to know how many milligrams of fluoride there is that we will need, to fluorinate at a level of 1 milligram of fluoride per liter. Then having the milligrams of fluoride, we will change them to grams of fluoride. And then once we have the grams of fluoride using the mass percent composition of fluorine in NaF, we can get the mass of the compound we need to pour in that water. So the solution will look like this. So let me show that. So the given amount is the 1,500 liters of water. So that's in the numerator. That's what you start with. Multiply by the first conversion factor that comes from the level of fluoridation that we want. And so we want the 1 liter on the bottom so that we can cancel liters of water, and the 1.0 milligrams of fluoride on top. This way we will know our mass of fluoride needed, but we need to convert the milligrams into grams. So the next conversion factors does that, changes the milligram into gram. And we have the 1 milligram on the bottom and the 0.001 gram on top so that we can cancel milligrams. The final conversion factors should cancel the grams of fluoride and change them to grams of sodium fluoride. And so for this, we use the mass percent of fluorine in NaF, and it's 45.25 grams of fluoride per 100 grams of NaF. And so we have the 45.25 grams of fluoride on the bottom, so we can cancel grams of fluoride. And we will be left with grams of NaF as the unit. And if you do this in your calculator, so it's 1,500 times 1 is not needed, so times 0.001 times 100, and then divided by 45.25. The calculator answer is 3.314917, etc. Here, both given amounts are given with 2 sig figs. The 1,500 has 2 sig figs, and the 1.0 milligrams of fluoride per liter has also 2 sig figs. Everything else is exact numbers, except for the percent composition. The 100 is exact, and the mass of fluorine per sodium fluoride is 4 sig figs. So anyway, the given amounts of 1,500 is limiting to 2 sig figs, just like the 1.0 milligrams of fluoride. So we need to keep 2 sig figs. And so we keep the 3.3 grams of NaF. What comes after the 3 is a 1, so we keep it a 3. So that would be the mass of sodium fluoride that should be added to the 1,500 liters of water so that it's fluoridated at a level of 1 milligrams per liter.